talk about some more properties of liquids, and this is a little bit more details about how intermolecular forces affect vapor pressure, the boiling point, and then how we can use the Clausius Clapeyron equation. We're going to start with talking about how intermolecular forces affect vapor pressure, and to do that we should really review what vaporization means. So vaporization is the phase change between the liquid state and a gas state. Now, we're not calling it a gas right now, we're calling it a vapor, because a gas is usually just in the gaseous state. A vapor is a gas that is in equilibrium with its liquid. So the difference there is a gas is just a container of gas, and a vapor has some liquid in it, and then some gas particles probably above the liquid because a gas is less dense. So this is how we kind of define a gas. This is a vapor. Really, they're the same thing. There's just a little bit of context there. Vapor means that it has some liquid next to it. So vaporization is taking a liquid and making it into a gas. We're going to make it into a vapor here because it's still in equilibrium with the liquid. And anytime we are taking a liquid and making it into a vapor, what we're doing is we're really moving the molecules apart from each other. And to do that, we have to break intermolecular forces. So the process of vaporization takes energy, and so we call it endothermic. We're putting energy into the liquid and breaking the intermolecular forces, the attractions between the molecules, and then the molecules can move apart and they can become a vapor. The energy required to do that is called the heat of vaporization. Sometimes we write it like this, the delta H of vaporization, or we call it the heat of vaporization. And it just means how much energy it takes to break those intermolecular forces enough to put enough distance between the molecules that they become a gas. Now, the more attracted the molecules are to each other, the higher the delta H of vaporization is, the harder it is to separate the molecules from each other. Once the liquid particles move away from each other and become part of a gas above the liquid, then because they're a gas, they're subject to all the normal gas laws that we know. So the ideal gas law, Dalton's law of partial pressures, all those apply to them once they've become a gas. Now let's look at what we have when we have a closed system. So these are just Erlenmeyer flasks. I'm going to talk about them. They kind of go in time. We're moving in this direction. So we're going to start with this Erlenmeyer flask here. It has a cork in it, or a stopper, and that's so that when we produce a gas, or the liquid produces a gas, it can't leave the container. So that's a closed system. At the very beginning, we just have liquid down here at the bottom. And even at room temperature, there's some kinetic energy there. And some of the liquid molecules are going to evaporate into the gas phase. So that's what we see here, is we see liquid water molecules moving into the gaseous phase. And we're just using water as an example here, but this would happen for any liquid. So in the very beginning, all that's happening is evaporation, liquid molecules becoming part of the vapor phase above that liquid. But over time, water molecules are going to kind of crowd up here, and there's not going to be any more space for liquid molecules to go into that vapor phase. It's going to be very crowded. So that's what we're starting to establish here. Here we have evaporation happening, but because it's starting to become crowded up here, liquid molecules from the vapor phase are coming back down into the liquid phase. So that's what we call condensation. So in this point, at this point here, we have evaporation and condensation. So in the very beginning, it's just evaporation. Then it gets crowded, and we have evaporation and condensation. And then eventually, we reach this place called dynamic equilibrium. And during dynamic equilibrium, we have evaporation and condensation. That's right here. But they're happening at exactly equal amounts. So for every one that comes up, one has to come down. And that's the equilibrium part. Equilibrium means equal rate of change. What equilibrium doesn't mean is that there are the same number of gas particles as there are liquid particles. Okay? There's probably always going to be more in the liquid phase than there is going to be in the gaseous phase, just because gases are a lot less dense. But equilibrium means that the rate of change is the same, so the rate of condensation is equal to the rate of evaporation, but it doesn't mean that there's equal amounts on both sides of that surface. Now, why we care about equilibrium is because, like we said in the beginning, in the first one, there's just evaporation. In the second one, there's more evaporation, but now some of them are also condensing. And here we've reached equilibrium. Okay. During these two, the amount of gas up here is changing quite a bit. So here, they're evaporating up into the gas phase, and so the amount of gas is changing. Here, the amount of gas is also changing because things are evaporating and a few are condensing. But here at equilibrium, for every gas particle that makes it down into the liquid phase, one makes it from the liquid phase up into that vapor phase. And because it's a 1-to-1 ratio there, the amount of gas is constant. And that's where we like to work. We like to work at a point of equilibrium because in all these other situations, the moles of gas is changing, and so it's really hard to calculate things like pressure and other kind of gas characteristics there because the moles of gas is changing. But at equilibrium, the amount of gas is constant, so the moles of gas is constant, and it's much easier to do our gas law calculations at equilibrium. Once those gas particles are in this vapor phase, so we've created a vapor phase above our liquid, once they become part of that vapor, they, like we said, follow all the gas laws. So these gas particles are exerting a pressure on their container, and that's called the vapor pressure. The more molecules that are in this vapor phase, the higher the vapor pressure. That's the same thing as like Avogadro's law, which is saying that the more moles of gas, the more volume and the more pressure they're going to exert. So those vapor molecules, once they've come from the liquid phase and gone to the vapor phase, they exert this thing that we call the vapor pressure. Now, vapor pressure is the same thing as pressure. So it's just the pressure of the gas. It's also the same thing as the partial pressure. So when we were doing calculations to talk about like the partial pressure of water, that's also the vapor pressure of water. Once things have settled down and we've reached a point of equilibrium, that's just called the equilibrium vapor pressure, that is the vapor pressure that we like to work with. If we're not working with an equilibrium vapor pressure, things are going to be changing so fast that our calculations are not going to be accurate. Things are changing so fast that even if we do a calculation, it's going to be different in just a second. So remember, at equilibrium, the rate of evaporation equals the rate of condensation. So that's what we define equilibrium as. And then we measure the vapor pressure, and that's the pressure we do calculations with. So let's talk about how intermolecular forces influence vapor pressure a little bit. We know that vapor pressure comes from liquid molecules that have become part of a gaseous state that we call a vapor. So these are my vapor particles up here. If the intermolecular forces between those molecules are very strong, the molecules are going to want to stay really close together. They're going to want to stay in the liquid state. So if we have really strong intermolecular forces, that means that not many will become a gas. And because there aren't many gas particles, we're going to have a low vapor pressure. So things with strong intermolecular forces tend to have low vapor pressures. Another way of saying that is a low rate of evaporation. Things that don't evaporate very much don't vaporize very much, and so those are the things with strong intermolecular forces. That also means that they have very high boiling points. A high boiling point means that it takes a lot of energy to take them from this bulk liquid state and produce a gas bubble and take it to the vapor state. So that's vaporization, just boiling something. If it takes a lot of energy to do that, we say that it has a high boiling point. So high boiling points mean that it's hard to make them into a vapor. Because it's hard to make them into a vapor, those molecules have low vapor pressures. So all the opposite things are true for things with weak intermolecular forces. And those weak intermolecular forces that we're talking about are things like dispersion forces. Okay, so those are our weakest of our intermolecular forces. Things that only have weak intermolecular forces aren't particularly attracted to each other. And so they're really pretty willing to become a gas, so to move apart from each other. And because they're willing to become a gas, a lot become gas particles. So they become vapor, part of the vapor phase. And because that's true, a lot of them move into the vapor phase. There's a high vapor pressure. That means that they have a high rate of evaporation. And things that evaporate really easily, we call them volatile. I know the word volatile means like you think they're going to blow up or something, but in chemistry, the word volatile just means that it evaporates really easily. You're probably pretty aware of some volatile compounds that you have in your everyday life. Any liquid where if it's in a container and you open up that container, you can smell it right away. That's a volatile compound. So you might be thinking about things like vanilla, for example. As soon as you open a container of vanilla, you can smell it from like a room away. Or things like fingernail polish remover, which is acetone, that's really volatile. You can smell that right away. But anything that produces a gas and then reaches your nose quickly, those are our volatile compounds. And those volatile compounds are things with weak intermolecular forces and low boiling points. When we talk about boiling point, I just wanted to talk about what boiling actually meant, and then we'll get into what boiling point means. And so I want us to do a little bit of a visualization here. You're going to think about, you get a pot of water, you put it on your stove, you turn it on. Your recipe says that you need to boil the water, and so you're standing there and you're waiting for your water to boil. And I know that sometimes it's hard to be patient, but think about how you would know that the water is boiling. So pause for a second and think about 3 different ways that you could tell that your water is boiling. What observations would you make? Now, what I usually hear people say are things like they saw bubbles. Great, okay? Other people say that they saw steam. Some people say that they put a lid on and the lid started to rattle, like the bubbles were pushing the lid up. Okay. Sometimes people say things like it boiled over. That's the same thing as like a lot of bubbles. Those are all observations that I've heard people say when they're thinking about how they would know that their water is boiling. And these are all true. You can tell that water is boiling by seeing all these things. What I want to point out is that none of these observations had anything to do with a temperature. If I'm walking into my kitchen and I'm trying to figure out if my water's boiling, I just look at it. I don't stick a thermometer in it to try and figure out if it's boiling or not. I just use my eyes. So when we talk about what's boiling, temperature doesn't usually come into play. Now, all of these things that we're saying, so bubbles, that's going from the liquid phase to the vapor phase. So that's just seeing molecules do that. Steam is observing a vapor. The lid's starting to rattle. That's the vapor expanding and pushing the lid out. And then boiling over again is liquid going to the vapor phase. And because vapors are less dense, it's kind of pushing the molecules all over the place and it's boiling over the top. So all these observations are really observing a vapor, observing a gas. Now, if all our observations about boiling are about making a vapor, I kind of wanted to talk about what's happening in our pot of water and how we see that vapor being produced. So this is my pot of water here, and this represents like my stove down here, so I'm heating it up. And if I'm heating it up, I'm giving the liquid molecules more energy, and I'm breaking some of the intermolecular forces, or at least weakening them. And when that happens, the liquid molecules, so these are going to be my liquid molecules down here, when I give them energy, they start to move apart from each other. So instead of being closer together, they're trying to move further apart. They do that just because they're moving around more and they don't feel the intermolecular forces as much. Now, as they move apart, at some point they're going to get far enough away from each other to produce a vapor. So even though they're in the liquid phase, they produce like a little bubble of vapor down there. And that bubble of vapor exerts a vapor pressure. So this is a vapor. And those are the little bubbles that we see forming kind of at the bottom of our pot. Now those bubbles are going to have to stay down in the liquid until the vapor pressure becomes high enough that it is bigger than or equal to atmospheric pressure. Once our vapor pressure becomes high enough, the bubbles can float to the top and they can become part of the gas around our pot here. And they become part of the atmospheric pressure. But it takes some energy to raise the vapor pressure enough so that it reaches atmospheric pressure. So we define normal boiling point as the temperature at which the vapor pressure of our molecules is equal or greater to atmospheric pressure. When that happens, vapor bubbles will form in the liquid and they will rise to the top. So you have to kind of think about it as the liquid molecules have to have enough energy so that they can become a vapor, and then that the vapor pressure will rise enough so that they can leave the liquid phase. And I think, again, it's kind of weird that boiling point, which is defined as a temperature, isn't a specific temperature. It is really dependent on this situation, the vapor pressure equaling the atmospheric pressure. So anytime that's true, that's what we call the normal boiling point. And atmospheric pressures are pretty constant in a location. If your ears aren't popping in your kitchen, your atmospheric pressure is pretty stable there. But at different locations, like for example, at the top of a mountain or deep down in a valley, at the top of a mountain, so if you're standing up here on top of a mountain, you literally, between you and the top of our atmosphere, have less air molecules pushing down on you. And so this is low atmospheric pressure. And if you're in a valley, like a really deep valley, like Death Valley, for example, you have more air molecules pushing down on top of you, and this is a higher atmospheric pressure. Now that's the same thing as if you've ever experienced like swimming in a swimming pool and you swim down to the bottom of the swimming pool and your ears start to hurt. That's because there's more water molecules pushing down on you. And so that's the same thing that you're feeling when you go down into a really deep valley. You just don't feel it as much when you're in air because water is so much more dense than air. Water has so much more of an effect. So it only takes about 10 feet of water to make our ears hurt, but it would take, miles deep down to make our ears hurt if it was just air. And because the atmospheric pressure is different at different locations, that means that the boiling point is going to be different at different locations. Because again, boiling point is just where the vapor pressure meets the atmospheric pressure. And if the atmospheric pressure changes, that means the amount of energy that it takes to make that pressure high enough is going to change, and the temperature is going to change. So boiling point is variable depending on what the atmospheric pressure is. I want to look at some data about how elevation and atmospheric pressure affect boiling point here. So we have some information about just some cities, we have their elevations, and we have their boiling points. I also wanted to add one more to this list, something that I looked up. So in Death Valley, which is not really a city, but it's an area, the elevation is below sea level. It's about 280 feet below sea level. And the boiling point is just a little bit higher than it is in San Francisco, kind of in our area. It's actually about 100.3 degrees Celsius. So we'll take that into consideration when we look at this trend. So what we can see is that as elevation goes up, boiling point goes down. So this is the lowest boiling point. This is the highest elevation at Mount Everest. Now I want to tie in atmospheric pressure to this because it's true, we have elevations, but elevation and atmospheric pressure are inversely proportional. So I'm going to write in some atmospheric pressures here. In San Francisco at sea level, they're about 14.7 psi, so that's just about 1 atmosphere. Up at Mount Everest, it goes all the way down to less than 5 psi. So that's about a third as much pressure exerted on you at Mount Everest as there would be at sea level, just because there's less air molecules sitting on top of you. And then in Death Valley, it's actually about 15.0 psi. So now here we can kind of directly see that the higher the atmospheric pressure, the higher the boiling point. The lower the atmospheric pressure, the lower the boiling point. And again, that just is because boiling point's defined as the temperature at which the vapor pressure meets the atmospheric pressure. And if the atmospheric pressure is lower, the temperature is lower. So it's interesting, if you were boiling something at Mount Everest, you would be boiling it at 76.5 degrees. And when you're cooking something at a lower temperature, it takes longer to cook. And that's why if you've ever, I'm sure you're not going to be boiling something at Mount Everest, but even places like Salt Lake City or anywhere high elevation, it has a pretty big effect. So even if you're like cooking your pasta in Salt Lake City, you're cooking it at almost 5 degrees lower than you would be if you were cooking it in San Francisco. And that just means it's going to take longer to cook things at higher elevations. And that's the reason why things like cake mixes and anything that needs to be baked for a little while and involves liquid, they have recipes that include high altitude baking instructions. And those high altitude baking instructions are always that you need to cook it for longer. And that's because you're cooking it at a lower temperature. And also that usually you need to add a little extra water. And the reason why you need to do that is because the longer you cook it, evaporation happens more and you lose a lot more moisture. So you need to kind of add that at the beginning so that you have the same amount of moisture at the end for your cake, and you've cooked it enough time so that you've given enough energy to kind of set up because you're cooking it at a lower temperature. So all of these boiling points, which one is the normal one? Well, technically, I know that in a slide before I said that the normal boiling point was the point at which the vapor pressure is equal to atmospheric pressure, but all of these, that's true for, and all of these boiling points, the vapor pressure is equal to atmospheric pressure, but only one of them is defined as the normal boiling point. The normal boiling point is the one where the vapor pressure is equal to 1 atmosphere. And that's actually at sea level. At sea level, we're at about 1 atmosphere. So this one is the normal boiling point for water. All these other ones are boiling points. It's just this is the only one that's the normal boiling point. So each substance only has one normal boiling point, and that's the point at which the vapor pressure is equal to atmospheric pressure, which is equal to 1 atmosphere. But that doesn't mean that there's not a relationship between boiling point and pressures. There's actually a relationship between the vapor pressure and temperature and the delta H of vaporization. Remember back when we were talking about what it meant to become a vapor, and we talked about how when you give the molecules more kinetic energy, so you're increasing the temperature, the number of molecules that are able to escape the liquid phase increases. And what that means is that if there are more molecules escaping the liquid phase and going into the vapor phase, that as the temperature is rising, as you're making more molecules leave the liquid phase, the vapor pressure is going to increase. So as temperature goes up, the vapor pressure is also going to go up. And really small changes in temperature make really big changes in the vapor pressure. So even if you just change the temperature a little bit, the amount of molecules that are in the vapor phase goes up drastically, and then the vapor pressure goes up drastically. So the amount that the vapor pressure goes up, again, depends on the strength of the intermolecular forces. If the intermolecular forces are weak, changes in temperature are going to have huge effects on the vapor pressure. If the intermolecular forces are really strong, you can change the temperature and the pressure will go up a little bit, but not as much as if the molecules were really willing to get away from each other, really willing to become a vapor. Those would make the vapor pressure go up really high. So let's look at some data. I just want to kind of look at this graph first. And what we have on this side is vapor pressure, and on this side is temperature. And then we have a bunch of different compounds that we're looking at. Now for every one of them, we can see that as we're increasing the temperature, the vapor pressure is going up. So diethyl ether goes up really fast, ethyl alcohol goes up a little bit slower, water goes up a little bit slower, and ethylene glycol goes up the slowest. What this graph tells us is that ethylene glycol is the least affected by temperature. Even if we increase the temperature quite a bit, the vapor pressure goes up, but not as drastically as like diethyl ether. So ethylene glycol is less affected by temperature. That means that ethylene glycol must have strong intermolecular forces, and diethyl ether has low, weak intermolecular forces. And there's one other thing I want to point out on this graph, and it's this line at 760 millimeters of mercury. Now that's a special place because it helps us identify normal boiling point. Remember, normal boiling point is defined as the temperature at which the vapor pressure is equal to 1 atmosphere. So what we're seeing here is that diethyl ether, its vapor pressure is increasing as we increase the temperature. When it gets to 760, that's when it's going to boil. And we can actually mark on here the temperature. Maybe that's about 35 degrees. So about 35 degrees is going to be the normal boiling point of diethyl ether, because that's the temperature at which the vapor pressure has reached 1 atmosphere. Now, if we're trying to predict how the vapor pressure is going to change with temperature, there's an equation called the Clausius Clapeyron equation that allows us to calculate this. Its form is a little bit complicated. It's saying that the natural log of the vapor pressure, so not this vapor pressure, but the natural log of it, is equal to the negative delta H of vaporization. That's the same thing as delta H of vaporization, like this, divided by RT. This is the gas law constant. And it's the 8.314 joules per mole K version, not the 0.08206 liters atmosphere per mole K version. And then this is the temperature in Kelvin. And then this is a constant. Sometimes we write that constant as B, like this, but they're really the same thing. Now what the Clausius Clapeyron equation is good for is predicting how vapor pressures will change with temperature, which means that it can help you calculate a new boiling point at different pressures. But it's also a way that we can figure out what the delta H of vaporization is. And to do that, we need to make this thing called a Clausius Clapeyron plot. And you're going to do that actually in your lab. Now when you make this plot, you plot the natural log of the pressure. So you take a bunch of pressure data and you find the natural log of it. You take a bunch of temperature data and you do 1 over the temperature. You get your data points. You make a best fit line, and the slope of this best fit line is equal to the negative delta H of vaporization divided by R. Now R is a constant, so if you rearrange this equation, you can say the slope, which is going to be a number, times R is equal to the negative delta H of vaporization. And if you want to make it positive on this side, you have to move the negative to the other side. So you can take pressure and temperature data, and you can use that to find the delta H of vaporization. That's actually how they find delta H's of vaporization for like the appendix in your book. It's one of the easiest ways to be able to calculate that number. Now say you don't want to do a lot of data points. You don't want to have all these data points. Say you only want to do maybe 2 data points, just enough to make a line. There's also another version of the equation that allows you to do the same type of calculation with just 2 pressures and 2 temperatures. So this is the Clausius Clapeyron equation in its 2-point form. 2 points meaning you just need 2 pressures and 2 temperatures. Now, in a way, this feels a little bit like a changing conditions problem for a gas law. Like you have an initial pressure and an initial temperature. If you change the temperature, how does the pressure change? That kind of thing. And we're going to treat it the same way. So you need kind of a known first set, and then you can change something, and you can see how another variable changes. So let's do a little example problem here. It says the normal boiling point of methanol is 64.6 degrees. Now, recall that normal boiling point means that the vapor pressure is equal to 1 atmosphere. So just in that statement there, we've already got our first pressure and our first temperature. Now, the problem also says, given that the heat of vaporization is 35.2 kilojoules per mole, so that's the delta H of vaporization. Calculate the vapor pressure, so we're looking for our P2, and of methanol at 12 degrees, so this is our T2. So I'm going to clean this up a little bit, just so that we can see the variables we're looking at. We know that our first pressure is going to be 1 atmosphere. That's the same thing as 760 torr or millimeters of mercury. We're looking for our P2. Our T1 is 64.6 degrees Celsius. I know that I'm going to need to put that in Kelvin. Our T2 is 12 degrees Celsius. I'm also going to have to put that in Kelvin. And then I have our delta H of vaporization, which is 35.2 kilojoules per mole. So what I'm trying to find is my P2 there. And the equation that I know that has to do with 2 pressures and 2 temperatures and the delta H of vaporization is the Clausius Clapeyron equation. So I'm going to write that equation out. So that I know what I'm working with. Like this. Okay. And it looks like I have my P1, I have my delta H of vaporization. R is a constant, 8.314 joules per mole K. And I have both temperatures. So it looks like I have everything that I need to find my P2. So I've cleaned this up a little bit again, just so that we can keep track of things, and I have my equation written here. What I'm going to do next is I'm actually going to put the numbers into the equation and start on the algebra. So I'm going to start with the natural log. I'm looking for P2. My P1, I could either put this in as torr, and I would get torr out, or if I put in atmospheres, I would get atmospheres out. It doesn't really matter which one you do. It's going to come out exactly the same. So I'm just going to put in 760 there. The negative delta H of vaporization is 35.2 kilojoules per mole. And my R is 8.314 joules per mole K. Now, if I'm using joules as my units for R, I need to make sure that my delta H is also in joules so that they cancel out. And what I can see is that this is in kilojoules. So I need to convert that to joules. That means multiplying it by 1,000. So this would actually be 35.2 times 1,000 joules per mole. So that's going to be that. And then my temperatures, I converted those to Ks. You can see, so my temperature 2 is this, and my temperature 1 is that. So 1 over T2, 337.8. Now I know it's going to be tempting to maybe do some algebra right here if you're kind of algebraically minded. I do suggest that you actually do this part on your calculator first, get a number, and then multiply it by this part. When I did that on my calculator, I got that the natural log of P2 over 760 torr was equal to negative 2.31 on my calculator. Okay, so now what I'm going to do is I'm going to get rid of that natural log on both sides, basically. So if I need to get rid of natural log on your calculator, if you do the second natural log button, that should be e to the x. So e to the x is the inverse of natural log. So if I want to get rid of the natural log of both sides, basically I'm doing e to the x of both sides. On my calculator, I typed in 2.31, and then I pressed the second natural log button, which means e to the x. And what I'm doing there is I'm doing e to the negative 2.31. That's what my calculator understands that as. So algebraically, what that works out as is P2 over 760 torr. And then what I got on my calculator was 0.0993, some other numbers past that. So now I've gotten rid of that nasty natural log, and now I have just this. I'm trying to find P2. So what I'm going to do is I'm going to multiply each side by 760 torr. And when I do that, I'm running out of room just a little bit, but when I do that, I came out to P2 was equal to 75.4 torr. So great, we've got a P2. Let's think about whether that number makes sense. We kind of started this conversation with calculations talking about how as the temperature goes up, the vapor pressure should go up. That works in the opposite direction too. So if temperature goes down, the vapor pressure goes down. In my problem, I went from a high temperature to a low temperature. So my temperature was going down. Did my pressures go down? Well, I started at 760 torr. I went down to about 1/10 of that. So yes, I would say that the vapor pressure did go down. That matches kind of the concept behind the Clausius Clapeyron equation. And sometimes it's nice when you do kind of a long calculation like that and you're wondering, you know, did I get anywhere close to the right answer, to go back and kind of check it with the concept. So when you're doing Clausius Clapeyron equations or any work with it, whatever happens to your boiling point, so if the temperatures are going down, the pressure should also go down. If the temperatures went up, the pressure should also go up. So in this video, we talked about the relationship between vaporization, vapor pressure, temperature, and intermolecular forces. We also talked about what it meant to establish equilibrium and what normal boiling point meant. And then we talked about the relationship between the vapor pressure and temperature, and the delta H of vaporization, which can be summed up in the Clausius Clapeyron equation.